Okay. Okay, perfect. So, welcome to our 8th lecture. So do you see the slides? Perfect. Yeah, so sorry for the confusion. We were before the semester we were moved into this room, and then they told me, okay, we have 1 week or 1 day where this room is not available, and then I forgot. But okay, so this week we're gonna make a big leap in terms of complexity or the types of networks that we can build. And so just as a kind of recap from last week. So last week was all about convolutional neural networks and residual connections. So we started out with residual connections, and which was basically this idea of kind of growing the function space in a more controlled way so that we don't forget any kind of previous state, and we only kind of refine our answers as we're kind of building deeper and deeper layers. And so with this, we could basically build arbitrarily deep networks without losing any type of learnability. And then the next thing we added was convolutional neural nets, which was this idea of kind of sliding these filters around like a 2-dimensional grid or 1-dimensional grid, whatever the dimensionality of your data is. And the idea here was that basically we added kind of more domain knowledge into the way we build our neural networks, which is kind of translational equivariance and invariance. And with these two ingredients, we then built ConvNets, which are kind of the main driving architecture behind computer vision for a long time. So nowadays there are a few different approaches to this, but it's still dominant. So I just wanted to kind of recap kind of over the last couple of lectures what we achieved. So we started with this idea of universal function approximation, and so in some sense you could imagine you're done. So for any type of RN, any high dimensional data, we can map using a network into some scalar quantity, and this is something we can learn to, for example, to make predictions in this high dimensional space. And in the principle, like a single layer, multi-layer perceptron, so just a single hidden layer, was totally sufficient to do any type of approximation with enough data. We could just basically learn anything that we wanted to. And so then the question is, okay, why do we need to do more at all? And then the next step was basically that we discussed, that going deep is very beneficial, because deep networks, by keeping the number of parameters constants, are much, much more expressive than shallow networks. And so we can learn more easily. We can learn more complex patterns with fewer parameters. And so that's why we added not only one hidden layer, but multiple hidden layers. Okay, so then was also the question, okay, are we done? And then this is where last week's lecture came in. Basically, then in order to go arbitrarily deep, we had these residual connections. And so we are starting to complicate the architecture, one by one. And it's all kind of not because theoretically it's not possible to learn, but more because it makes learning easier. And so we added these residual connections. And then with our convolutional neural nets, we are basically starting to adapt the structure of the network to the type of data that we have. So, it's true that in some sense, like an image is a very high dimensional, just one vector, right? So we have like, or MNIST is 784 inputs, so 28 times 28 pixels. So you can think of it as just one huge vector, but it's somehow not really adapting to the type of data we have. We know much more about how these input signals are arranged, and so we, for example, know that they're in like a 2-dimensional grid, and so we want to exploit all of this domain knowledge about the type of data that we have, and this is what we call inductive bias. So sorry, this should be inductive bias, not implicit bias. So basically we had two key ideas for convolutional neural networks. We had this idea of local connectivity. So here we're exploiting our domain knowledge that in order to kind of extract And so this is the idea behind weight sharing. And so then we had like lots of discussions that this kind of yields translation equivariance first, that the filters they move together with the input signal. So if we have like an edge detector, but we move the image behind it, then the edges will also move, right? So this is translation equivariance. But then if we're about, classifying an image, we had these pooling layers, and they kind of progressively add translation invariance to the network, so that in the end, if we want to classify in an image, okay, is there like some type of galaxy in the image? We don't really care where in the image a galaxy was. The task is just to figure out, is there a galaxy in the image, and it doesn't really matter where. And so that's so we want to have often translation invariant networks. And so we're starting to add these types of goals and domain knowledge ideas into the structure of the network. And so this is a very powerful idea. Okay, so then this is basically now starting to be a more general trend. So we have specific data types, and then for any type of specific data type, we can choose an like an appropriate neural network architecture that matches this type of data, right? And so there's a kind of like a lookup table, and then very often there's an associated symmetry that is crazy language models that you might have seen over the last couple of days. This is all based on transformers, and so we might, if we have time, talk about these in this lecture as well. But this transformers only kind of correspond to a very specific type of graph. If you have any type of graph, which is what we're going to discuss today, is like a graph neural network. Deep sets is also something we're going to discuss today. And so they're all kind of related to permutation symmetry. And then another topic we haven't really touched is like sequence-like data. So if you have sentences, or you have like a video, or any time series, any type of causal sequence, this is then there's also a network that is associated to this, called recurrent neural networks and LSTMs and so on. And we'll also talk about these in a future lecture. But so generally, kind of if you do like a machine learning problem, what you should be doing is that you should think about, okay, what type of data do I have, and what network architecture matches this type of data the most. It's true, like in principle, you could just use like flatten the data completely into like one huge high dimensional vector, and then apply like a MLP on it, but then you'll need a humongous amount of data in order to do this, or maybe it's not even possible, because as we discussed for CNN, like if you two animals in the middle, GNNs and deep sets, and then RNNs we're going to discuss in the next lecture. Okay, so then the question is, so how do we arrive at graph neural networks? Is basically this idea of generalizing these powerful ideas that we had for convolutional neural networks. So basically, for convolutional neural networks, we had we exploited like the specific spatial arrangement of the signals. So we had our image, which usually has three types of channels: so red, green, and blue, right? But so each of these channels is like a whatever some two-dimensional matrix, which with some width and some height, right? And then we had our third dimension with just the channel, and then we applied these filters that you see on the right by sliding these filters around these images, right? And so the powerful idea here is that these filters, so the amount of memory that we need in order to process an image didn't really depend anymore on the size of the image. So we started from, if you want to have like a 28 by 28 image, then you have like an MLP that needs 784. If you have like 1,000 by 1,000, you need like we have the same type of things where we have like a number of objects and they're somehow interconnected. So there's some notion of spatial arrangement or like vicinity at least, but they're not arranged in the super kind of regular two-dimensional grid, right? And so we want to generalize from pixels that are connected kind of in this super regular way to sets of generic objects that are connected in some arbitrary way, and that connectivity somehow encodes what we know about the data. So which things are close to each other, which things are not so close. And so we'll basically discuss now how to do this. And so the language to do this is the language of graphs. And so you might have seen graphs in some other contexts before, but basically the graph is defined by two type of pieces of information. They're basically defined by the set of nodes. So like which objects are we talking about? And then a set of edges, which are the connections between the nodes. And so here you see basically a graph with 6 objects, and then different objects are connected more tightly than others, right? So you see some nodes have many connections. So like this one at the bottom has, for example, 3 connections, and the one just to the right of it only has a single connection. And so somehow there's like a direction implied, so where you go from one node to another node, but just because one node is kind of connected in one direction to one node doesn't mean that it's connected in the other direction. And so, for example, if you have like a graph where you have like a parent-child relationship, just because whatever person X is your mother, it doesn't mean that you are person X's mother, right? So there's some kind of directionality, but then very often there's also kind of like a notion of undirected edge, where the direction really doesn't matter. So it's just a matter of, are these two things related? Yes or no. So if I'm related to you, you're related to me, and doesn't really matter. And so this is an example of an undirected edge, right? Okay, so then we can discuss some special cases for graphs. So you can have either kind of no connectivity at all. So this is just kind of like a bag of objects. So you only have the nodes, there are no edges at all. Or the other extreme is basically that you have like a full graph where basically every edge is connected to everybody, which is basically almost, kind of like a trivial statement where kind of you're not really making kind of like a statement about like spatial or connection or vicinity, because everybody is close to everybody, right? And so then these two cases are then also treated by different types of architectures. What we want to do is we want to attach now data or signals onto this graph. And so there are multiple ways in which we can do this. So we can, for example, attach features like feature vectors onto single nodes. And so let's say we have like a three-dimensional feature. You can imagine, okay, you have a graph of persons, and then you can think of three types of features for persons, like hair color, age, height, or something like this. So you have, for every node, you have like pieces of information which you can encode like individually into a high dimensional vector, right? And so then every node has like its own little vector attached to it. And so this is one type of data we can attach to the graph. Another type of data is edge features. So you could also say, okay, there's like some information that is encoded on the edge, which basically characterizes the type of relationship that is kind of meant by this edge. And so we'll discuss some examples in a bit, but these are basically the ways we can attach data to the graph. And so here, like an example, so one of the biggest examples of graphs and machine learning are social networks. So you might imagine, you have things like Twitter or Facebook and so on. And so social networks, the name already implies they're very easily modeled as networks or as graphs, right? Where the individual nodes are the persons, and then the edges, they signify somehow like a relationship between them, right? And so what can we think of as node features? So what type of data can we attach to the graph? So we can, for example, attach age or height, hair color, location, and so on. Like, if you're tracking someone, what is like the GPS location of a person or something like this. And then you might also have things, edge features. So, just saying two people are related, not every relationship is the same thing. So for example, there might be categorical features where you have like the same way that for, like MNIST digits, we had categorical digits as labels, for example. We could also have like categorical features on the edges. For example, what is the type of relationship? Are you like friends, or are you relatives, or this is your mother, whatever. So you can have like different like categorical features. Then you might also have floating point features, right? So these are for example, like the strength of the relationship. Are you very, very good friends or not so good friends, and so on? Or you might have, like the length of the relationship. Have you been friends forever? Have you been friends since yesterday? So there are different types of data, and it doesn't really matter what the type of data is. It's kind of outside of the scope of this learning problem, how to represent this data. In the end, you want to represent this data as a high dimensional vector. For example, you could even have like a profile picture. It's like an image. And so we know through CNNs how to encode an image into a high dimensional vector by for example, doing convolutional networks until we only have like a single signal with many, many filters, right? And then this would basically encode like an entire image into a single high dimensional vector. And this is, for example, something we could attach to the graph at a single node as node features, right? And so there are no limits on what kind of data you can kind of attach to the graph. Okay, so then another example is, for example, molecules. So this is very kind of vibrant field of using graphs and machine learning recently. So there's lots of excitement about using machine learning for drug discovery and so on. And molecules, they're really naturally described as graphs because you have like the individual atoms and they're connected by bonds, and so there's a very natural map between the individual nodes, which would be the atoms, and then the edges would be the bonds. And then you could even have, so I didn't put here edge features, but you could have edge features like, is it like a double bond or a single bond or so on. You could have edge features as well. And then kind of what is the relevant node features for like a molecule? It's probably, what is the position of the individual atoms in the molecule? And so, for example, in protein folding, like one of the big problems is, okay, how does the protein fold? So what is like the final like low energy configuration spatially, where all of these atoms sit? And so the position is a very important feature. And you can see that clearly somehow the position of one node needs to be connected to the position of the next node, otherwise the bond breaks. And so somehow the signals have some correlation the same way that, for example, in an image, the signal have correlations where, if you're like in a patch of grass, all of the pixels there are lightly green, right? And so so there's some relationship between the type of signal that is on the pixels between and the local connectivity. And so here it's the same idea. So you have like a correlation between like the position of the individual nodes and the connectivity of the graph. Okay, so then another node feature you might, for example, have is, what is the type of atom? So is it like hydrogen or, carbon or oxygen and so on? And this, of course, really encodes what type of atom or molecule this would be, right? And what the functionality of these things is and so on. All right, and so then my favorite application, of course, particle physics. So we have particle detectors, and so one of the things that we have in particle detectors that usually we describe them as kind of three-dimensional cameras, right? So this is an example of a neutrino telescope. So you have cosmic rays coming from the outer space, and then they hit this telescope, and then so this is a telescope that is at the South Pole called IceCube, and so it's basically like a big like block of ice, so like a cubic kilometer of ice, so 1 kilometer wide and long, and then 1 kilometer deep. And so how does this block of ice become a telescope? We basically put holes into this block of ice, and then we have like submerge strings of particle detectors into this ice in some pattern. Right, and so these strings have at regular intervals, they have sensors, right? And they might not be kind of exactly positioned in a way that is like a Cartesian grid. So like a CNN would not be a good way, but there are spatially, of course, somehow, situated. And so this spatial, information is, of course, important if you're trying to interpret signals. So you have like a cosmic ray coming from like some direction. And then depending on which modules it passes by closely, those modules will light up, right? And then so it's basically, so this is, we're taking like a three-dimensional picture of the cosmic ray, but the picture is not in the form of like a 2- or 3-dimensional image, right? So it's not like an image or voxels and so on. But it's more like you have these strings of sensors, and then they're somehow situated somewhere in space. Okay, so this is one particle detector. So this is also from research in another group at TUMS, and they're really into using graph neural networks. This is from my research. So this is the kind of like a similar idea, but at the Large Hadron Collider, where we have like particles, and then they fly. So we create like a new particle, for example, like a Higgs boson or something like this. It decays, and then the decay products, they fly outwards, and then we have like a detector sitting kind of everywhere around the collision point, and then it starts interacting with sensor material there as well. And so you can see, so in this case, you have like a particle going from the bottom to the top, and then as it's traversing this detector, it will interact with different types of sensors and so on. It will also light up different kind of sensor components. But these sensors, they're also not, I mean, they kind of are conceptually like a camera, but it's not like a pixel-based camera where you have like a constant alignment of grid, because it also depends on how you can construct the detector, and you also need to move cables through the detector, and so it's a more irregular arrangement. But you have kind of the same idea. You have like multiple layers of sensors, and then there's kind of cover some kind of area at each layer, and so we can describe this very nicely as a graph. And then we have a signal on the graph, which is like the strength of the interaction of the particle, with this specific sensor that is at this position. Okay, so then like the easiest graph that we have is of course like an image, and actually you can just think of the image as a graph as well, right? So just because they're very, very regularly aligned doesn't mean they're not like a set of objects. So they are a set of objects, but the connectivity is super regular. And so how can we think of an image as a graph? We basically think of, so the object that we're thinking about is like an individual pixel, right? And so for each, and so the nodes are the individual pixels, and then for every node we have a three-dimensional signal, kind of the strength of red, green, and blue, right? So the color of the pixel. And then, so now we have our set of objects, our nodes. And now the question is, okay, how can we convert this into like a graph, or what is the graph structure here? And so basically, when we're discussing convolutional neural networks, the graph is supposed to encode like what is the local neighborhood of like any given position. And so the way that we structure, for example, this 3x3 kernel, the local neighborhood were kind of these 8 neighboring pixels, right? And so if we want to somehow encode this spatial connection, we would, for every pixel, we would add these 8 connections, right? And so we can do it for 1 pixel, and then we can generalize it. What is important is that some of these edges also have some type of edge feature, in the sense that there's some kind of orientation associated with this as well. It's not just that so there's a difference whether or not like 2 pixels are connected and one is to the right of each of the other, or the other one is on the top of each other. So not all edges are the same, and so this is kind of like important, and it's also one of the reasons why we need to think more harder on how to generalize this for general graphs where we don't have this kind of orientation signal anymore. But okay, we can kind of add these edges, and then we can do it basically for every pixel, and then we have like a very, very regular graph that is super, super tightly connected, at least at the local level, right? And then in principle, we can process this just as a graph, or we can process this as an image, and these 2 things should ideally produce similar results. Okay, so then okay, we have our graphs, we have our data, so we somehow, like in our little statistical learning diagram, we have the most important ingredient of machine learning, the data, right? So and again, so the structure of the graph is not necessarily part of the data, but it's something that is externally given. What is important is the signal on the graph. It's the same way that like for MNIST images, the graph was always the same, was always 28 by 28 pixels, and there was local connectivity. But then what was important is that the signal on this regular graph changed, and then this changed. And so what we were trying to learn was to interpret the signal on the graph. What is true is that on convolutions, we could then extend, once we learned it on like a small image, we can apply these kind of filters also to a larger image without changing the network. And so in some sense, we can generalize from one graph structure to the next. But for many, many cases, the actual graph structure doesn't change, and only the signal is changing. And so then the question is, okay, what type of problems are we trying to solve on the graph? And there are basically 3 types of problems that are usually discussed. So there's kind of like a node level problem, edge level problem, and like a graph level problem. And so let's say, what do we have for like node level problems? So the idea here is that we want to do like node level prediction. Imagine we have some data on the graph, and then you want to predict, okay, is the person a student, yes or no, given on, what the signal is on the graph. So you might imagine you have like a graph with people with ages and, location and so on. And, it's not infeasible to imagine that from this type of data, is the person, very strongly connected to people in the same age range and so on, to see whether or not they're like a student or, are they in high school and these types of things. And so we want to basically make a prediction for every single node, right? And so the example here that I have is, okay, what's your favorite sports club? You could also imagine this is also easily predictable from, location data and types of things like that. Okay, so then like an edge level prediction is trying to predict, what the type of, what the label is on a specific edge. And so you might, for example, have like a social network, and then kind of the question you're trying to answer, okay, I see these people are connected, but are they connected because they have like a kind of first degree family relationship? So are they kind of mother and child or so on? Or, are they just friends, right? And so this is also probably something that you could try to predict. But now you're trying to predict data on the edges, right? And it doesn't necessarily mean that in the data that you have on the graph, you have edge features. You might only try to predict it from node features. But in general, between graphs, there's also like a duality between edges and nodes. So every graph that you can describe as like a set of edges and nodes, you can flip it around and make every edge a node and every node an edge. And so that's called a dual graph. And so the difference between like edge prediction and node prediction is not so big. And so we'll basically focus not so much on edge prediction, or talk a lot about what to do with data on edges, because in the end you can always kind of rephrase it as data on nodes. But in general, like you have these types of learning problems as well. Okay, and so then the kind of most common use case maybe is graph level prediction. And so this is the generalization from trying to do digit classification on images, or figuring out, okay, what the content is of an image. And so there we had like this idea, okay, we have our like in an image we have our regular grid, and then we have a signal on this grid. So we have for every point in the pixel, we have our RGB signal. And then what we're trying to predict is not necessarily, okay, what is like a property of a single pixel, but we're trying to make like a global statement, okay, what is some label for all the pixels together, right? And so what we're trying to figure out is, okay, is there like a certain digit in the image, yes or no, or is there like a galaxy, or is this a Higgs boson? And so it's like a statement about the entire graph, right? And so this is basically then what we're trying to do with our graph level prediction. Okay, so then now we have our data kind of arranged on our graph, but handling graphs in the computer program is like this is not super easy. So we want to somehow find data structures that encode the graph in a more amenable way for a computer. And so for this, it's important to give the graph like an order. We need to somehow name the individual nodes or number the individual nodes. But what's important is that this type of order is completely arbitrary, right? So it doesn't really, so the real data is like this type of data where we don't have any kind of numbering on the nodes, but now I always need to tell you, okay, it's the node like on the top and to the right, or the bottom left node and so on. And so this becomes very tedious very quickly. And so it would be nicer to just like give names to these positions and just say, okay, node 1 has these this yellow vector, or node 5 has this green vector, and so on. And but what's important is that this order of how we label the nodes is just a choice that we make in order to make our lives easier for data handling, and it's not really something that is inherent in the data. And so whatever we're trying to do, whatever prediction we're trying to make on the graph shouldn't really depend on how we, assign these names or what the order is of these nodes. And so this is exactly where permutation and variance comes in as a concept. And so we'll talk about this for a bit. So now I'm running out of battery again. Do you have a? Perfect. Excellent. Actually, no, yeah, I got it. Okay. Okay, so this is why is it? Okay, so yeah, so this is an important point, and it's kind of like the entire point of this lecture is that this order assignment is just something spurious, and we ideally have networks that don't care about this order. And okay, so the way that we can, but let's imagine we're fixing some order. So we'll call this node on the bottom right 1, and then we have 2, 3, 4, 5, 6, right? But you could choose any other order. But once we have an order, we can actually represent all of the data that we have on the graph as a matrix, right? And so that's nice because we know, okay, one of the best things that these deep learning libraries can do for us is like things, manipulating matrices, matrix multiplication, and so on. And it's just like a very regular way to kind of represent this irregular data. And so given that we have like this type of order, this is the matrix that we would get. So we have our green vector at the top, then the yellow, so node 2, and then node 3 is kind of like the teal color, blue, red, and violet. Okay, great. So, but then the point is, okay, we could also use like a different order, and it doesn't really matter. So you just pick some kind of order that you want, and then depending on what the order is, you have like a different data matrix. But it's still kind of like a nice matrix that allows you to handle this data in a useful way. Okay, so so this is kind of encoding the data that we have on the nodes, but of course, one of the most important things of the graph is the connectivity of the graph. But it turns out that we can also represent the connectivity in the graph as a matrix, and so this is called the adjacency matrix. So basically, we have n nodes, and then we have n times n kind of pairs of possible connections, right? So every node, at least hypothetically, could be connected to every other node. And so we need to reserve somehow n by n slots. And then what we can do is basically say, okay, is node 4 connected to node 5? And then if yes, we put like a 1 into this matrix. And if node 5 is connected to node 4, we put a 1 in this matrix as well. And so you can see kind of what the difference is between directed graphs and undirected graphs. For directed graphs, the adjacency matrix might not necessarily be symmetric, right? Because just because node 5 is connected to node 4 doesn't mean that node 4 is kind of also connected to node 5. But for undirected graphs, the adjacency matrix is always going to be symmetric. So the transpose of this matrix is going to be equal to the matrix itself, right? And so this is kind of like an adjacency matrix. And so now you can think of, okay, so conceptually, it's nice that we have it as a matrix, and we'll use this picture kind of most of the time. But one kind of more computational efficiency question is, so you see, okay, you have like n squared slots, right? But you have only kind of 2 non-zero elements. And so if you would store it as a normal matrix where you have like an n by n, you kind of store n by n numbers, and so most of these numbers are 0. It's a very inefficient way to store a matrix. And so the software tools that usually try to encode a matrix, they might kind of pretend as if there's an adjacency matrix, but internally they will store it as a sparse matrix where they only encode, okay, which positions are actually non-zero, and it's applied that everything else is zero. Okay, so but this is our adjacency matrix. And then so we can see, so this was like this single edge that we had. And so if we only had basically this single edge, this is what our adjacency matrix would look like. If we now kind of take all of these edges in account, our adjacency matrix looks a little bit more complicated. It's still kind of sparse, but you see it's symmetric. And then, for every, you can kind of count for every row, like let's say you have node 3, you see on the graph, you have 3 connections. So there are 3 incoming edges on node 3. And then if you look at the row kind of on 3, you have like 3 black markers, right? And so basically by summing over either the rows or summing over the columns, you can basically also get what's called the degree of the matrix, which is the number of incoming connections that you have for every single node. Okay, so this is the way that we encode the graph structure also as a matrix, and so this is great. So we have our data as a matrix, we have our adjacency, our kind of graph structure as a matrix, and so basically we reduced everything again. We are only dealing with more or less regular matrices, which is really nice for processing with a computer. All right, so then what's kind of interesting, so we have the same problem that now, okay, so this is the adjacency matrix for like a specific choice of ordering of the nodes, but you could have chosen a different ordering and it wouldn't make the adjacency matrix wrong. So there's like this level of ambiguity, what even though like 2 adjacency matrices are different, doesn't mean that they describe different graphs, right? And so by just choosing a different ordering, you're just commuting either the columns or both the columns and the rows at the same time, and this then produces a different matrix. And so this is something that we need to keep in mind. And so there are basically 2 effects of permutation. So the permutation will affect the data representation, so the our data matrix by switching the rows, right? And then it will also change our adjacency matrix by permuting the rows and the columns. Okay, so how can we okay, so first a few examples. So here we have like a diagram from the play Othello, so which like Shakespeare, you have lots of people kind of involved and they have like different types of relationships. And so you can kind of track, okay, as you're going through the play, who's interacting with whom, right? And then you can kind of create a graph of like the social network in this play of Shakespeare. And then this type of graph then corresponds to an adjacency matrix, which looks something like this, right? And so this is our hyper regular image. So if you consider an image as a graph, we had like these 8 little connections for every pixel. And so now you can kind of see that this super strong regularity also encodes itself in the structure of the adjacency matrix, where you can see you have like these diagonal bands. And so basically the 2 off diagonal, so the one that are kind of closest to the diagonal, they're the ones that kind of are kind of the cross, so right, left, top, bottom, and then the diagonal bands that are a little bit further out are kind of the diagonal connections that you have kind of to the top right, top left, bottom right, bottom left. Okay, so but then you can kind of already see that the adjacency matrix captures all of this regularity information as well. Okay, so then the question is, okay, how can we express permutations? So as we said, so we need to somehow represent our symmetry. So what we're interested in, so this is something we discussed last lecture, we can somehow formulate mathematically what it means to be equivariant or invariant to a symmetry, but in order to do this, we need to somehow represent what the operation does in our representation of the data. And so that means that if we represent our data as a matrix, we should somehow, or as a vector, we should somehow be able to represent our operation, our symmetry operation, which in this case would be permutation, as a type of matrix operation. And so it turns out that that's very easy to do. And so a permutation matrix is also just a matrix that has basically all zeros, and in every row there's only one point that is non-zero, and this basically encodes like which position gets swapped for which position. So we can go through this, and so basically permuting just means the matrix multiplication with such a permutation matrix. And so we can see whether or not this is true. And so if you do like a matrix multiply, so you kind of go row, you multiply rows by columns, right? And so you do like, okay, you have 0, 0, 0, 0, 0, and then the one that you pick up is the red box, right, at the bottom of the input vector, and this then ends up at the top, right? So the kind of the fifth row is mapped to the first row, right? And so this is because in the permutation matrix there's basically, at the 1, 5 position, like an entry, right? And then the next one is 0 again. And so you're picking up only the red signal for the first output slot that you have. And then for the second, it's the same thing. So here we want to pick up the 6th signal. So it's all zeros until the very end, and the last box is 1. And then we go through this entire matrix multiplication, and just by multiplying this permutation matrix, we arrive at the permuted data vector, right? And so this is nice. We don't need to really kind of operate on the graph. We can just operate on our matrix representations of the graph, and then we're fine. Okay, so then how do adjacency matrices change? So as we said, these matrix, the adjacency matrix can is basically swapping columns and rows, and so that just means that we are basically doing like a change of basis using an orthogonal matrix, which is our permutation matrix. And so by swapping kind of our, we have our original adjacency matrix, and by adding like the permutation matrix on the right and on the left, we can basically then, extract our new adjacency matrix. And so we have a very structured way to go, from data, in one, assignment of the nodes to data and the other assignment of the nodes. Okay, so so why do we need this? So basically because we want to somehow encode what we mean by symmetries. And so in order to, if we want to have like a node level function, right? So what the function that we want to have is a function that should be permutation equivariance. So what does it mean? Permutation equivariance, so this is something we discussed last lecture as well, means that basically there's a commutation relationship between doing the symmetry operation and applying the function. So either, applying the function on the transformed input should be the same as applying the symmetry operation on the original input. F of P of X is, so if we first permute and then we apply our function, and that should be the same as if we just apply our function first and then permute, right? And so let's say we have a function that does like a node level assignment, and so we have our original graph on the left, and then our output of the function should be either classifying the function as blue or green nodes, right? What should happen is if we are just changing the assignment of the node, so the order in which we are assigning nodes, the labels should kind of do the same type of operation, right? Or they should move kind of in the same way. And so we can either say, so we have our input in a certain ordering, so where we have red, orange, violet, and so on, or we have like a different type of ordering, and then we're starting whether or not we permute first and then classify, or first classify then permute, should be the same type of operation. Okay, so this is what we mean by permutation equivariance. And so here is basically, if we want to just classify like the entire graph, like is this like in this graph, like is this like graph of like a clique of students, or is this like a family or something like this. We want to make some statement about the graph overall. So then what we want to do is like a permutation invariant object. And so basically permutation invariance means that applying the function on the original data and applying the function on the transformed data should produce the same type of result, right? And so because the result should only depend on the connectivity of the graph and should not really depend on how we label the graphs in order to represent our data as like a data matrix. Okay, so then this is permutation invariance. And so let's see, so what we're going to discuss is how can we build functions that have these symmetries kind of baked in. And so the way that we can do this kind of easily is that we can consider graphs that don't have any type of connectivity. So just like a bag of objects. And this is what we would call sets. So let's say we have like this set of 6 objects. And so how do we do like a permutation invariant function on it? So it's actually very easy. We can, so because we don't have any connectivity, the only thing that we can do once we have a signal on the set, so every node has some kind of data attached to it. Really, the only thing that you can do is to kind of process this data element-wise, right? So you can, because you don't know, which nodes or like no nodes interact, so you can just process each object individually, and so we can basically just represent the data into some other form, and basically means, okay, maybe you have like some kind of weighted combination of age and height. Of, we discussed, is someone like a good basketball player and so on. And it's just like a different like data processing of each node. And so this is trivially permutation equivariant because if you change the node order, of course, like your data processing output will change accordingly because there's no connectivity really involved. And so this gives you like a permutation equivariant, output. And so let's see how we get something that is permutation invariant. Basically here, what we can do is we can take all of these outputs that we have from our node, like element-wise processing, and we can pool them together the same way that we pooled in convolutional neural nets using a permutation invariant pooling operation. And so like a very popular permutation invariant pooling operation is summation. So A plus B plus C, or C plus A plus B, or B plus C plus A, they're all the same, right? So summation of n things is a permutation invariant property. The sum doesn't depend on the order of in which you're summing the objects together. And so by taking such a permutation invariant pooling operation, you trivially get like a permutation invariant representation of all of your input sets, right? And so we've somehow embedded our original signal into some like a representation that is by design permutation invariant. And then once we have this, we can then further process our data. So let's say we kind of process our data first individually, then we do our pooling operation, which encodes or forces permutation invariance. Then we can continue processing our data, for example, using a neural network. And the output is basically guaranteed to be permutation invariant because we forced it through this pooling operation. This kind of structure where you have element-wise processing, invariant pooling, and then further processing using, for example, a neural network, this is called a deep set. And so this is kind of interesting. It was, the paper came out in 2017, and this is the gist of the paper. You're just summing these things up. But I mean, it was basically like a nice way to encode, okay, how do you encode things kind of as a set? Because before people would just choose like some kind of ordering that maybe made physics sense. So for example, you order particles by energy and then you're embedding them into some high dimensional vectors, and often that makes sense, but that doesn't really capture this domain knowledge that we have that the order shouldn't really be important. And so by using this simple trick, you can basically encode like a set of objects into a permutation invariant thing. And so the output vector will represent the set as a whole without any notion of order. And so basically, here's an example of using deep sets in physics. So this is again for particle physics. We have a lot of like particles flying out kind of from the collision point. And so we want to often reason about like sets of particles that are kind of flying close by. And so, but these particles might or might not be related. And so there's definitely no type of connectivity between two particles. They're just independently flying through the detector. And so what we want to do is, but we want to somehow, find the data representation that, represents this, n tuple of tracks, for example. And so in order to do this, for example, at the LHC, we use a deep set. Okay, so then so this is basically, okay, we solved our problem of permutation, invariance, and equivariance for graphs that are trivial, where there's no connectivity at all. And so now we'll try to generalize, okay, what do we do once we do have connectivity? And so we want to somewhat generalize this notion that we have with convolutions. And so convolutions were important because they introduced this idea of local data processing, where we only need to do something at every location, and doesn't really matter what is happening elsewhere. And this was really the key to get scalability. And so if you want to kind of process a very large graph, ideally you also only process the local neighborhood, because the idea is, okay, the graph encodes which signals in like this entire bag of objects are important and which are not important. And the ones that are important should be kind of only like a few hops away from you. And so the question is, okay, how can we somehow extend this idea of a convolution to kind of graphs that are not as regularly structured as images? Okay, so then just a reminder, so how do we think of convolutions? Basically, what we thought of convolutions is kind of that we have our filter bank, and then this is shifting left and right, right? So we had our weights on our filter, and then if we wanted to get an output, we multiply the data with the weight, and then we're collecting multiple weighted inputs into our node, right? But for this discussion, it's actually useful to think of it a different way, where you keep the filter fixed and you're sliding the data, across it. And so the thing that you're moving is the data and not the filter. And so you can say, okay, so how do we get an output for an image? So we have our fixed filter, and so there's like for like the data position 0, there's some weight that we have, and then we shift the data, and this is what we multiply with like another weight, and then we shift the data again, and we multiply it with a third weight. And then once we have our products of weights and data items, we just sum them all up, and then this is the output that we get at this position, right? And so the way that you can think of it in this picture is that you're basically summing from top to bottom, where you're multiplying W0 to X1, or W1 to X2, and W2 to X3, and then you're basically summing all of these signals together. And then if you have like a bigger filter, you'll have more shifts and so on. And this is a useful way to think of kind of convolutions as well. And so basically, in order to kind of get to graph convolutions, the way that we can think of is basically that we can think of this xi plus o. So in the convolution, we had our weights, and then we have our shifted data that is being multiplied, and then we're summing over different types of shifts, right? And so let's think about, okay, what does it mean for, what does object xi plus o mean? So it's basically the data at a shifted position. And so we can basically think of xi plus o as being the result of applying like a kind of atomic shift multiple times. So shifting once, shifting twice, shifting 3 times, shifting 4 times. And so xi plus 1 is, applying a shift once. And so we represent the shift as like this S of X. And then xi plus 2 is applying the shift twice, and so on and so on. And what this type of construction gives us is that basically you can think of convolutions as a type of polynomial, where basically you have powers of the shift operation, and then every power of the shift operation is then multiplied by some weight, right? So just to reiterate this, so we start with our kind of expression of a convolution, xi plus k times wk. And now we say, okay, xi plus k is basically you start from xi and then you shift k times the data. And so you have, you're applying this shift operation multiple times. So that means you have like the power of the shift operation. And so you apply the power of the shift operation and then you multiply it by some weight. And so it's somehow it's like a polynomial of this shift operation, right? And the coefficient of this polynomial are the weights wk, right? And so the higher you have, the higher orders in this polynomial, they basically correspond to collecting signals further away because you need to shift more and more in order to kind of accumulate this data. And okay, so then how does it look like in our case? So we have our original data, which is basically applying the shift 0 times, and it's just the original data. Then we apply the shift once, then we apply the shift twice, and then whatever we have at our position that we're interested in, we're multiplying this with the coefficients of this polynomial, which is W0, W1, W2, and then we're summing all of these things up. And so this is basically then the construction that allows us to extend the idea of convolution to convolutions on graphs. So let's kind of look at a very simple graph which is connected kind of linearly, and this will kind of bring us back to our standard convolution. So what does the adjacency matrix look like for this graph on the right? So notice it's a directed graph, and so the adjacency matrix is not symmetric. And so that means that so we have basically like an off diagonal. So we have like entries on the diagonal shifted by one thing. So we always have neighbors connected to each other, and then just for convenience, we close the loop at the bottom, and so the last node is connected to the first node. So you have kind of like a ring. And so this is the adjacency matrix. What the adjacency matrix looks like. And so now the question is, okay, how do we represent a shift so this idea of like a shifting operation? And actually it's very easy because it's just like multiplying the adjacency matrix with the original data. And so if you apply the adjacency matrix on this data, x1, x2, x3, x4, you basically, you're shifting the input, and because you're for the first row, you're picking up the second element. For the second element, you're picking up the third element of the input, and so on. And so you're basically shifting everything kind of once from to the top, and then because of the circular nature, you have the x1 at the bottom there, right? And so we can basically use the adjacency matrix that we have that encodes our graph to kind of represent this core operation that we need in order to implement convolutions as we had them in the convolutional neural networks, by just saying, okay, we just apply the adjacency matrix on our data matrix, and this is our shifting operation. And then what we call convolutions is basically, powers of this shifting operation, or applying this shift multiple times. Okay, and so this is then what basically generates what we call a graph filter, and it's the generalization of a convolution on a grid. And so we had our kind of convolution on the left hand side. We have like this polynomial of shifting the data multiple times to like either to the right or to the left, and then multiplying this with some weight. And so it has like this type of polynomial shape. But then we can extend this because now we know how to generalize the shifting operation, because the shifting operation only means multiplying like the something like the adjacency matrix onto the data matrix. Then we can just use the same type of construction on any type of graph. And so then we construct our polynomials again, and this is what we call a graph convolution. And so that's very nice. So we needed to go like a little bit of a detour, but we managed to basically find like a notion of convolution that doesn't really depend on kind of like this idea of sliding a filter across, but it's more, you know, kind of taking the graph structure into account. Okay, so let's see what this means for undirected linear graph. So the normal convolution, as we have them in convolutional neural network. So for this, we need to use a directed graph because we want to shift only the data in one direction. But now we can say, okay, let's say we have a graph that is very similar, but it's now, there's an undirected edge. So there, it goes both ways. So that means that the adjacency matrix is basically symmetric, right? And so we have not only our original adjacency matrix where we had like this diagonal and then this piece at the bottom left, but now we're taking the transpose and we add it as well. And so then this gives us this more symmetric adjacency matrix because we have now these undirected edges. And so what does it mean to do the shifting operation now? Basically, it's shifting the data, but it's shifting from multiple directions at once. And so for the first slot, so let's say what is x1 receiving after the shifting operation? It gets like the input from x2, and it gets an input from x5. So basically, it gets the input from its neighbors, right? So and then what is happening? But it's both weighted by this weight w, right? And so now we can see, okay, for position 2, which inputs are relevant for position 2, or what is like the result of applying the shift once? But basically, it's accumulating the input signals from x1 and x3, right? And for x3, it's connecting the inputs from x2 and x4. So you always kind of get signals from both sides of your connectivity. And so that's kind of interesting. That's not exactly the same as a standard convolution as we had it originally. And so because you notice, so we now get multiple inputs by just shifting, so to say, once. Yeah. Sorry? Yeah. So I think I forgot one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Yeah, exactly. Yeah, but I mean the concept stays the same. But it's kind of interesting that by shift once. So in the original convolution, in order to get multiple multiple signals, we needed to shift multiple times. So you shift once, you shift twice, and so on, and then you pick up different links from the neighborhood. Here, by just shifting once, you get kind of signals from multiple directions at once, but they're all the same type of signal. They're all weighted by the same weight. And so let's see what this basically corresponds to. You can kind of imagine you have like a convolution where this convolution gives you kind of the same signal from the neighbors with the same strength. And then the only thing that is different is that the signal on the neighbors might be different on the right and on the left, but the scaling factor W with which the signal is being processed is the same. Okay, so then if you wanted to kind of convert this into like the normal picture of a convolution as we had it before in our kind of convolutional neural networks, it's basically so this single shift operation, but for a unidirected graph is the same as having like a symmetric filter that has the same weight at the right and on the left, and there's zero weight in the bottom. So there's no self-link. So you're basically computing the new input to be the output of or the sum of the right-hand side and the left-hand side. And so you're collecting signals from the neighborhood. Okay, so then what does it mean to then shift multiple times? So shifting multiple times basically just means you're collecting more information from a larger and larger neighborhood, which is the same idea behind like our original convolutions. When we had our original convolutions here, basically shifting multiple times meant we're collecting signals from like points that are farther away. But now if we have a undirected graph, we're basically collecting from both directions always at the same time, but now from like a larger window, right? And so you can see now there we basically get the like a signal from the right, kind of the red box on the right kind of that flows into our output box after shifting twice. Then the middle box actually that ends up in our output box twice because there are two paths to get there. And then the left-hand leftmost red box that is highlighted that also ends up. And so if you wanted to convert this again into like the picture of a normal convolutional network, it would basically be like what's called a dilated filter, where you have like multiple zeros, and then you have like W, 2 times W in the middle, and then W again, but then there are zeros in between. And so you get what's kind of like radially symmetric filters, where you kind of always cover a bigger and bigger field of view, right? And so this is kind of interesting, and so you can actually play with this yourself. If you click on the slides and this link, there's a kind of like a nice widget that you can play with, and you can basically take this polynomial in kind of graph shift operations, and then you see that how changing the different coefficients of this polynomial will change the like effective filter, like translated back into our original convolutional network language, right, where we have our small filter that we would then kind of move overall. Okay, great. So this is then our graph convolution. And now, because all of this kind of shifting operation is just kind of multiplying this adjacency matrix with our data matrix, we can then extend it not only to our undirected linear graph, but we can extend it to any graph that we want at all. And so we can, for example, look at this graph where we have 5 nodes, and then see, okay, which nodes provide an input to our node that we have labeled 1. So the 1 is labeled to like a local neighborhood, and so to nodes 2, 3, and 4. And then this will basically then give us our combination of signals from the local neighborhood. Okay. All right. So one of the things that we didn't discuss, so now you notice in our shifting once operation, we somehow completely forgot the input that we have from our original node. So we only collect inputs from the right neighbor and the left neighbor, and somehow we forgot exactly what is the input or like the data that we had at this node before. And this is not great, because probably you want to somehow incorporate your own state with the states of your neighbors. And so it's important to maybe adjust this adjacency matrix or with entries on the diagonal in order to not forget what is happening on your node, that you have the state that you have anyways on this node. And so we can basically adapt our adjacency matrix by adding what's here shown in red, like a diagonal entry for your adjacency matrix. And so these basically corresponds as if you had a graph that had self-links. And so you have like a messaging pathway from you to yourself. All right. So then one of the, so what should this adjacency matrix or the shift operation then look like? There are multiple options on how you can design these shift operation matrices, and every type of shift operation matrix will correspond to a certain kind of signaling pattern. But what's useful is, so you have like the diagonal, which is the identity, which are the self-links, and then you have your adjacency matrix, so you add them two together, so you have self-links and the adjacency. And then these degree matrices, I mean, not so super important for you right now, but it's basically just to make things numerical stable, because the more links you have coming in, the higher if you're summing all the signals, the higher and higher the signal is going to be. So you want to somehow normalize on the number of signals that you receive, and so you want to divide by basically the number of links that you have and how many neighbors you have, and then you're basically taking the average of the different signals that you get from your neighborhood. All right, so so we now basically constructed something like a convolution. Let's see whether or not it satisfies our permutation equivariance idea. So as we said, okay, we want to somehow find like a way to process our data without kind of depending too much on the ordering in which we label the nodes. And so here, remember that the under permutation, what is happening is that the adjacency is matrix is being basically there's a change of basis in the adjacency matrix by taking the permutation matrix from the right and from the left, and then the data matrix is changing by applying the permutation matrix from the left. So you go from X to P for X, and for the adjacency you go from A to P transpose. And so if we use our shifting matrix or shifting operation, if we design it like this, where it's basically more or less the identity plus the adjacency matrix, it's clear that our shifting operation will just also transform like the adjacency matrix, where the shifting operation in the transpose picture is going to be the original shifting operation with the permutation matrix from the right and from the left. Right, and then you can fairly easily see that by plugging these in, so the function applied on the permuted graph, so that means the permuted data and the permuted shifting operation is the same thing as if you would basically apply the function on the original data and the original shifting operation and then permute, right? And so you have this nice equivariance picture where, doing the symmetry operation first and then applying the function, which is the f of x prime and s prime, or doing the function first and then doing the symmetry operation are the same thing, right? And so with this, basically, you have like a data processing paradigm on the graph that is permutation equivariant. Okay, so then, we wouldn't basically talk about neural networks if we didn't have any nonlinearity. So nonlinearity is important, and so this same way that we added, when we build convolutional neural networks, we had our convolutions, and then we added a nonlinearity to it, and then another convolution, another nonlinearity. Basically, what we can do here is we have our graph convolution, and then we add our nonlinearity, which we apply element-wise, and this doesn't destroy the permutation equivariance at all because it's an element-wise operation. And so this is then the basic building block of a graph neural network. You have our kind of signaling phase, which is this SXW, and then you have a nonlinearity which you apply element-wise. Okay, so then we can basically now generalize from our deep sets and CNNs, which we discussed before, to graph neural networks. And so graph neural networks are basically, we apply our graph convolution and then we apply our linearity, and it kind of sits between our convolutional neural nets, which we had on the right, where the operation is kind of the standard convolution and the nonlinearity. And then on the deep set side, we had like an element-wise processing, which itself might be nonlinear because it might be like a neural network that you're applying just on the data that's on each node. But then because there's no crosstalk, it's of course permutation invariant. And the graph convolution maintains the permutation invariance, but there is some kind of signaling between the neighborhoods of inside of the graph. Okay, so then the way that we build graph neural networks is just we do the same trick that we do always. So we have like a basic data processing paradigm, how we turn one type of data into the next iteration of the data by taking into account like some other signals in the vicinity, and then we can just do this multiple times, and we get basically deep networks by just stacking multiple layers of graph convolution and nonlinearity. And so basically what is happening, we have our original graph on the left, and then for every layer, like the graph stays the same, but then the data on the graph is changing. And what is happening is that the signals from the neighbors are starting to percolate into the graph, and you're collecting, the more layers you have, the more global information you're starting to collect, because the messages can it's basically like doing the shift operation multiple times. Okay, so then how do we then do our final learning task? So we do our, if we want like a node prediction, we just kind of then do like an element-wise prediction layer where we, so we have our final process graph, and then we just do like an element-wise prediction. So that might be a neural network or some like simple MLP. And if we want to do graph level prediction, we do the same trick as we had before with our deep set. We first pool everything in a permutation invariant way, and then we process the outgoing data maybe with some final neural network. And because of this pooling, so we went from permutation equivariant to permutation invariant, right? And then this is our final output, and this would be the prediction on the graph. And this prediction doesn't really depend at all on the ordering of the nodes, because all of this signaling pathway, all these like data changes in the data representation, they were kind of defined by the edges. And so this is the core data that's in the graph, and it didn't really depend on the ordering at all, right? Okay, so then I'll finish up. So we have our comparisons. On the left-hand side, we had our convolutional neural network, which is the same type of idea. We have like this data processing phase that is typical for deep learning. And then you have, which is just preparing the data for the final task that is doing the final prediction. And so here on the left-hand side, we had it for CNNs and images. And then for the right-hand side, we have basically for graphs, but it's the same idea. We have multiple passes of, preparing the data and finding good representations of the data on the substrate that we have. In this case, it would be a graph. And then we have our final prediction on the final process output, which then pools all the data together and then gives us the final answer. Okay, so then we can basically go beyond graph convolutional neural networks. They're the major architecture that we have, but they're not the only ones. And so you can kind of look at it as a much more general way, where you kind of think of like nodes passing messages to each other. And it's not necessarily like a graph convolution, but some other types of messages are being passed. And so these graph convolutional networks are just one instance of this much more general paradigm of message passing graph neural networks. And here you basically have three components. You have your nonlinearity, and then you have some kind of function that takes in your own node state, and then some pooled version of what the neighborhood is doing. And the way that the neighborhood is communicating to you is through some kind of messages, which might depend on kind of who you are and who your neighbor is, right? And so, but we'll not be able to go through this, but I encourage you to kind of click on these links. There are various ways. So they're convolutional. So convolutional is what we discussed, and then there's graph attention networks. And then like this much more general message passing idea, where you might have like a neural network predicting the message that you're sending from one node to the next, which is much more complicated. Okay, so this is, sorry for going over time for 3 minutes. So basically what we discussed is we made this jump from convolutional neural networks to graph neural networks, and it's a pretty broad generalization. And so in some sense, you can express almost every neural network architecture as a graph neural network with certain types of message passing and certain types of connectivity. But I wanted to re-emphasize that this only works if you really know what your graph is. And so the creation of the graph is often the most difficult thing in having machine learning on graphs, because this is really what defines on how the signals get processed and what it means to be in the neighborhood of some object. And so most of the graph neural networks applications, for example, in particle physics, it's like a lot of graph processing and finding on what a good graph is, and then okay, you run like some fairly generic GNN on it. But then, that's not the complicated part. The complicated part is finding out what the graph should be. Okay, so thanks a lot. And so next week, we'll talk about recurrent neural networks. Thank you. Yeah, I'll upload them today. Okay.